The end of the world is often imagined as sudden. An explosion, a flash of light, everything gone in an instant. But science tells a very different story. Earth is not fragile, it is temporary. And its end will not come from fantasy, but from real, measurable processes already written into the laws of physics. This planet has survived asteroid impacts, supervolcanoes, ice ages, and mass extinctions. Life has been wiped out before, not once, not twice, but 5 times. And each time, Earth continued, changed, scarred, but still here. So when we ask how Earth could end, we are not asking if disaster is possible. We are asking how it happens and why it is inevitable on long enough timelines. Some endings are slow, so slow that no one notices until it's too late. Others are sudden, violent enough to reset the entire planet in a matter of hours. And some are guaranteed, not because of human failure, but because of how stars evolve and how time works. Tonight, we're going to explore 10 real, scientifically possible ways Earth could end. No science fiction, no exaggeration, no imaginary threats. Only scenarios backed by physics, geology, and astrophysics. Some could happen in our lifetime. Some are millions of years away. And one is absolutely certain. This is not a story meant to scare. It's meant to explain, because understanding how Earth could end also explains why it has lasted so long, and why the choices we make now matter more than we realize. Let's begin with the most familiar threat, one that has already happened before.
Asteroids are not science fiction. They are leftovers, fragments of rock and metal left behind from the formation of the solar system over 4 billion years ago, and millions of them still orbit the Sun today. Most are harmless, some pass close to Earth, and a few are large enough to end civilization. We know this because it has already happened. 66 million years ago, an asteroid roughly 6 miles wide struck what is now the Yucatan Peninsula. The impact released more energy than billions of nuclear bombs. The dinosaurs didn't die from the explosion. They died from what came after. Within minutes, shockwaves raced around the planet. Earthquakes, tsunamis, wildfires ignited across entire continents. Then came the dust. Trillions of tons of debris were blasted into the atmosphere, blocking sunlight for years. Photosynthesis collapsed. Plants died. Food chains followed. 75% of all species vanished. Not because Earth exploded, but because sunlight disappeared. That event reshaped life on this planet, and it proved something crucial. Earth is not immune. Today, scientists actively track near-Earth objects, asteroids whose orbits bring them close to our planet. Thousands have already been identified. Most will never hit us, but statistically, one eventually will. It is not a question of if, only when. A modern asteroid impact would not necessarily wipe out all life, but it could end civilization. Cities flattened, global agriculture destroyed, supply chains collapsed. The most dangerous part would not be the impact itself, it would be the aftermath. Years without reliable sunlight, global cooling, mass starvation, a slow collapse of human society. This is why asteroid defense is one of the few planetary threats we take seriously enough to prepare for. Space agencies now test ways to alter asteroid paths, because unlike most cosmic dangers, this one is detectable and potentially preventable. But prevention requires time, and detection isn't perfect. A large asteroid approaching from the direction of the Sun could remain hidden until it's too late. Asteroid impacts are rare, but over long timelines, they're inevitable. Earth has been hit before, and unless something changes, it will be hit again. And that brings us to the next threat. one that doesn't come from space, but from deep beneath our feet.
Supervolcano eruption, the slow collapse. Not every planetary catastrophe comes from the sky. Some come from below. Far below Earth's surface, heat builds slowly, silently, over tens of thousands of years. And when it is finally released, the planet doesn't explode. It chokes. A supervolcano is not a mountain with lava flowing down its sides. It is something far larger, a massive underground chamber of molten rock stretching for miles, pressurized beyond anything we can control. When it erupts, the explosion is not measured in lava flows, but in climate change. The most famous example lies beneath Yellowstone National Park. It doesn't look dangerous. No smoke, no fire, no warning. But beneath the surface is enough magma to cover entire continents in ash. Yellowstone has erupted before, roughly every 600,000 to 800,000 years. The last eruption happened about 640,000 years ago. That doesn't mean another eruption is overdue, but it does mean this is a real geological process, not a hypothetical one. A supervolcano eruption would not destroy Earth instantly. Instead, it would trigger a chain reaction. First comes the explosion, an eruption thousands of times stronger than Mount St. Helens. Ash would shoot into the stratosphere and spread across the globe. Entire regions would become uninhabitable within days. Then comes the real danger. Ash blocks sunlight, not for weeks, for years. Temperatures drop worldwide. Growing seasons collapse. Crops fail across continents that were never touched by lava. This is called a volcanic winter, and it doesn't care about borders. Food shortages wouldn't be local, they would be global. Modern civilization depends on precise agricultural timing. A few bad harvests in a row could collapse supply chains. Mass migration would follow. Conflict would escalate. Not because Earth is dying, but because civilization is fragile. Life itself would survive. Microbes, plants, animals. Earth has endured supervolcanoes before, but human society, with billions of people and tightly connected systems, has never faced one. And that's what makes supervolcanoes so dangerous. They don't wipe out life, they erase stability, slowly, relentlessly, until the world that existed before no longer functions. Unlike asteroids, supervolcanoes cannot be deflected. They cannot be stopped. They can only be monitored. And even then, warning signs might come too late to prevent global consequences. Earth would remain, but the world we recognize might not. And that leads to the next threat, one that humans themselves have brought dangerously close.
Nuclear war, the self-inflicted winter. Unlike asteroids or volcanoes, this threat did not come from nature. It came from us. In less than a century, humanity learned how to release the energy stored inside atoms, and with it, we created the ability to damage the entire planet. A nuclear war would not end Earth by blowing it apart. The real danger comes after the explosions. Cities would burn, not just from blast waves, but from firestorms so intense they generate their own winds. These fires would inject millions of tons of soot and smoke high into the atmosphere, higher than rain clouds, higher than weather, into the stratosphere. And once that soot is there, it doesn't come down easily. Sunlight would be blocked, not everywhere equally, but enough to matter. Global temperatures would fall. Crops would fail. This scenario has a name: nuclear winter. Even a limited nuclear exchange between a few nations could trigger worldwide consequences. Computer models show that just a fraction of existing nuclear weapons could lower global temperatures for years. Not days, not months, years. Modern agriculture depends on stability, predictable seasons, Reliable sunlight, consistent rainfall. Nuclear winter breaks all of that. Growing seasons shorten, harvests shrink, food shortages spread. Starvation becomes global. What makes this threat especially dangerous is not just its power, it's its speed. Unlike climate change or volcanism, nuclear war unfolds in hours. Decisions made in minutes could shape the fate of billions. Earth itself would survive. The oceans would remain. The continents would endure. Life would eventually recover, but human civilization as we know it might not. The most unsettling part is how close this scenario already is. Nuclear weapons exist. They are maintained. They are ready. The only thing preventing catastrophe is restraint. This is a reminder of something crucial. Not all planetary threats come from the cosmos. Some are built quietly, piece by intelligent beings who underestimate their own power. And that brings us to the next danger, one that unfolds slowly, without explosions, but could permanently change Earth's future. Runaway climate feedback, a Venus-like future. Not every ending is loud. Some arrive slowly, quietly, until they become impossible to stop. Runaway climate feedback is not about weather. It's about systems crossing thresholds. And once those thresholds are crossed, the planet no longer responds the way it used to. Earth's climate is regulated by delicate feedback loops. Ice reflects sunlight. Oceans absorb heat. Plants regulate carbon dioxide. For millions of years, these systems have kept Earth within a narrow, life-friendly range. But feedback works both ways. When balance is lost, change accelerates. As global temperatures rise, ice melts. Dark ocean water replaces bright ice, absorbing more sunlight. That extra heat melts more ice. This is a feedback loop, and it doesn't stop on its own. Then there's methane. Locked inside permafrost and deep ocean sediments is a greenhouse gas far more powerful than carbon dioxide. As temperatures rise, methane is released. That release causes more warming, which releases more methane, another feedback loop. At a certain point, these loops can overpower natural stabilizers. Oceans warm and lose their ability to absorb carbon. Forests die and stop removing CO2 from the atmosphere. The planet begins heating itself. This is what scientists call runaway climate feedback. Not an overnight apocalypse, but a gradual shift toward a new equilibrium, one that is hotter, more hostile, and far less forgiving. We have an example of this outcome: Venus. Venus likely once had oceans, but a runaway greenhouse effect turned it into a world hot enough to melt lead. Its atmosphere became thick, toxic, and permanent. Earth is not Venus. Our distance from the sun is different, our oceans are deeper, our systems are stronger. But physics does not negotiate. If enough greenhouse gases accumulate, the outcome becomes inevitable. This scenario would not destroy Earth. The planet would still exist, but surface life, especially complex life, would struggle to survive. Oceans would slowly evaporate, weather patterns would become extreme, habitability would shrink to isolated regions. The danger of runaway feedback is not that it happens suddenly, it's that by the time it becomes obvious, reversal may no longer be possible. This is one of the few planetary threats that is influenced by human behavior, not because humans control Earth, but because we can push systems closer to tipping points. Earth has endured massive climate shifts before, but never with 8 billion people depending on stability. And that leads us to the next threat, one that has nothing to do with what happens on Earth's surface, but everything to do with what protects it from space. Loss of Earth's magnetic field. Stripped by space. Earth has an invisible shield. You can't see it, you can't feel it, but without it, life on the surface would not exist as it does today. This shield is Earth's magnetic field. Deep beneath our feet, liquid iron churns inside the planet's core. That motion generates a magnetic field that extends far into space, deflecting charged particles from the sun and from the wider galaxy. It is the reason our atmosphere is still here. We know what happens when a planet loses this protection. We've seen it before. Mars. Mars once had rivers, lakes, and possibly oceans, but its core cooled, its magnetic field weakened, and the solar wind did the rest. Over millions of years, Mars's atmosphere was stripped away, particle by particle. The planet didn't explode, it simply dried out. Earth's magnetic field is not permanent. It is weakened and strengthened many times throughout Earth's history. Sometimes it even flips. North becomes south, south becomes north. These reversals are natural and usually not catastrophic, but they reveal something important. The magnetic field is dynamic, not guaranteed. If Earth's magnetic field were to weaken significantly for a long period of time, the consequences would be severe. Solar radiation would penetrate deeper into the atmosphere. Satellites would fail, power grids would collapse, radiation exposure at the surface would increase. But the real danger lies in the long term. Without strong magnetic protection, the solar wind would begin to strip Earth's atmosphere. Slowly, relentlessly. Oxygen, nitrogen, water vapor, all would leak into space. This would not happen in a year or a decade, but over geological time, the effect would be irreversible. Oceans would evaporate faster than they could be replenished. Surface temperatures would swing wildly. Life would retreat underground. Earth would not die suddenly. It would fade, becoming thinner, drier, more hostile. A slow transformation from a living world into something far more barren. The most unsettling part? This process does not require disaster. No impact, no explosion, no warning. Just time. The good news is that Earth's magnetic field remains strong today, but its past tells us it cannot be taken for granted. And that brings us to the next threat, one that is not caused by Earth or humanity, but by the star that gives us life.
The sun's evolution. The guaranteed ending. Some endings are avoidable. This one is not. No matter what humans do, no matter how advanced civilization becomes, Earth's fate is tied to the life cycle of the sun. And that life cycle has already begun. The sun feels permanent. It rises every day. It has powered life on Earth for over 4 billion years. But stars are not eternal. They are born, they burn, and they change. Right now, the sun is in a stable phase called the main sequence. It fuses hydrogen into helium, releasing energy at a steady rate. This balance is why Earth is habitable. But hydrogen is finite, and when it begins to run out, the sun will change dramatically. In about 5 billion years, the sun will enter the red giant phase. Its core will contract, its outer layers will expand. The sun will grow, not slightly, but enormously. It will swell outward, possibly engulfing Mercury and Venus. And Earth will not escape unscathed. Long before the sun physically reaches Earth, the damage will already be done. As the sun brightens, Earth's temperature will rise. Oceans will begin to evaporate. Water vapor, a powerful greenhouse gas, will trap even more heat. A runaway greenhouse effect will begin. The skies will thicken with steam.
surface temperatures will soar. Liquid water, the foundation of all known life, will disappear. Earth will become uninhabitable hundreds of millions of years before the sun reaches its maximum size. At that point, life on the surface will be impossible. Only the deepest, most resilient forms of life might survive briefly underground. Eventually, even they will vanish. This is not speculation. It is stellar physics. We observe this process happening to other stars across the galaxy. The sun is not special. It will follow the same rules. Earth will not explode. It will not shatter. It will be cooked, transformed into a dry, lifeless world, orbiting a dying star. This scenario reminds us of something profound. Earth's habitability is temporary. It exists within a window of time, a narrow window in the lifespan of a star. And while this ending is far away, it is absolutely certain, which makes it unique among all planetary threats. But the sun has another side, one that could affect Earth long before it becomes a red giant.
Solar superflares. Civilization collapse without planetary death. The sun does not just shine, it erupts. Most of the time, these eruptions are harmless. Beautiful auroras dancing near the poles, a reminder that our star is alive. But occasionally, the sun releases something far more powerful, a solar superflare. Solar flares are sudden releases of energy caused by tangled magnetic fields on the sun's surface. They launch massive clouds of charged particles into space at millions of miles per hour. When these particles hit Earth, our magnetic field usually protects us. Usually. History has already given us a warning. In 1859, a solar storm known as the Carrington event struck Earth. Telegraph systems sparked, caught fire, and failed worldwide. Auroras were seen near the equator, and that was in a world with no satellites, no power grids, no global electronics. If an event of similar strength happened today, the consequences would be severe. Satellites would be disabled or destroyed. GPS systems would fail. Communication networks would collapse. Power grids could overload and shut down for weeks or longer. A true superflare, stronger than anything we've recorded, could be far worse. It wouldn't kill life directly, but it could erase modern civilization almost overnight. No internet, no banking systems, no transportation networks, no emergency coordination. Modern society depends on electronics working continuously. A large enough solar event could push systems beyond recovery. Transformers could melt. Replacement parts could take years to manufacture. Cities would go dark. Supply chains would break. Earth would still be alive. Forests would grow. Oceans would move. The planet would continue as always. But human civilization, highly connected and technologically dependent, would be thrown backward decades, possibly centuries. The most unsettling part? The sun shows signs that superflares are possible. We've observed sun-like stars releasing energy bursts hundreds of times stronger than anything our sun has produced in modern history. We don't know how often these events occur, only that they can occur. And when they do, they give little warning. Minutes, sometimes seconds. Solar superflares remind us that not all endings involve extinction. Some involve collapse, a sudden loss of complexity, a reminder that intelligence alone does not guarantee resilience. And that brings us to the next danger, one that is far rarer, far more violent, and far more final. Gamma-ray burst, the instant atmospheric killer. Some dangers don't give warnings. They don't build slowly. They don't leave room for response. They arrive at the speed of light. A gamma-ray burst is one of the most violent events ever observed in the universe. It occurs when a massive star collapses or when two neutron stars collide. In a matter of seconds, more energy is released than the sun will emit over its entire lifetime. These bursts don't explode in all directions. They are focused, tight beams of radiation shot across the universe like cosmic spotlights. If one of those beams ever pointed directly at Earth, the damage would be immediate. The burst itself would not burn the surface. Instead, it would strike Earth's atmosphere. Gamma radiation would tear apart nitrogen and oxygen molecules. That reaction would destroy the ozone layer, the planet's primary protection from ultraviolet radiation. Within hours, the atmosphere would change chemically. Within days, the surface would be flooded with lethal UV radiation from the sun. Plants would die first. Oceans would lose their plankton, the foundation of the marine food web. Ecosystems would collapse from the bottom up. This would not be localized, it would be global. Life would not vanish entirely, but complex life, especially on land, could face mass extinction. The most unsettling part? Earth would not see it coming. Gamma-ray bursts travel at light speed. There would be no advance notice, no buildup, just consequences. Fortunately, gamma-ray bursts rare, and they must be close enough and precisely aligned to cause catastrophic damage. But rare does not mean impossible. Astronomy has already identified stars capable of producing such bursts. Earth's survival so far may be a matter of geometry, a matter of orientation, a matter of luck. Gamma-ray bursts remind us that not all cosmic dangers arrive slowly. Some are silent, instant, and completely indifferent to what exists in their path. And now, we move to the next scenario, one that doesn't come from radiation or stars or volcanoes, but from something wandering.
A rogue planet enters the solar system. Not everything in space follows a neat orbit. Some worlds are homeless. Rogue planets, also called free-floating planets, are worlds that drift through the galaxy without a star. They are born in solar systems and then violently ejected by gravitational chaos. Today, astronomers estimate there may be billions of rogue planets wandering the Milky Way, invisible, cold, and unpredictable. Most of the time, they pass through space harmlessly. But if one ever entered our solar system, the danger wouldn't come from impact, it would come from gravity. Gravity does not need contact. A massive object passing nearby can quietly destabilize everything. Planets shift, orbits stretch, ellipses become chaos. Even a distant pass could disturb the delicate balance that keeps Earth stable. If a rogue planet passed near the outer solar system, it could disrupt the Kuiper Belt. Comets would be sent inward. A rain of impacts would follow over thousands of years. Not one extinction event, but many. If it passed closer, near Jupiter or Saturn, the effects would be faster. Gas giants could be pulled slightly off course. That small change would ripple inward. Earth's orbit could shift, closer to the sun, overheating the planet, farther away, triggering global freezing. The worst-case scenario would be a near pass, close enough to significantly alter Earth's orbit, not destroy the planet, but make it uninhabitable. Seasons would become extreme, climate systems would collapse, ice ages or heat waves would dominate permanently. Humanity would not see this coming early. Rogue planets are dark. They emit little to no light. They're detected only when they pass in front of distant stars. By the time one entered our system, warning could be limited. The good news? Such encounters are extremely rare. Solar systems are vast. Distances are enormous. But over cosmic timescales, even rare events become possible. Earth has survived billions of years because its orbit has remained stable. A rogue planet threatens that stability without ever touching us. And that brings us to the final scenario, one that is different from all the others because it doesn't require asteroids or stars or planets. It only requires intelligence without restraint.
Technological collapse, the choice-driven ending. This final ending is different from all the others. It doesn't come from space, it doesn't rise from Earth's core, and it doesn't wait billions of years. It comes from decisions. Technology is not dangerous by nature. It is powerful. And power, without coordination and restraint, can destabilize systems faster than any natural disaster. Modern civilization is deeply interconnected. Energy grids, communication networks, food supply chains, financial systems. Each one depends on the others. This efficiency gives us comfort, but it also creates vulnerability. A large-scale technological collapse would not destroy the planet. It would destabilize the systems that allow billions of humans to survive on it. Artificial intelligence is often misunderstood. It does not need to become conscious to be dangerous. All it needs to do is optimize the wrong objective too efficiently. Infrastructure mismanagement, automated financial collapse, resource misallocation, escalation of conflict. Small errors amplified at global scale. Technology can also accelerate other threats: nuclear escalation, environmental mismanagement, autonomous weapons, misinformation at planetary scale. None of these require malicious intent, only speed and lack of oversight. Unlike asteroids or supervolcanoes, this scenario does not follow a schedule. It follows behavior. It is not inevitable. It is conditional. Earth would remain, life would persist, but civilization, as a complex global system, could fracture, not with a single collapse, but through cascading failures. One system fails, then another, until recovery becomes impossible. What makes this ending unique is that it is the only one fully within human influence. We cannot stop the sun from aging. We cannot prevent rogue planets, but we can decide how responsibly we wield power. This scenario does not predict extinction. It predicts loss of complexity, a world where knowledge survives in fragments, where technology regresses, where rebuilding takes centuries. And that brings us to the final realization of this documentary. Final reflection: why understanding the end matters. Earth has endured unimaginable forces: asteroids, ice ages, volcanic winters. It will likely endure many more. The planet is resilient. Civilization is not. Most real endings of Earth are not instant. They are gradual. They unfold when systems fail, when balance is lost, or when time simply runs out. Understanding how Earth could end is not about fear. It is about perspective, because the same processes that can end our world are the ones that shaped it. Earth's future depends on three things: time, physics, choices. Two of those are beyond our control. One is not, and that may be the most important fact of all.